Welcome to my video on measuring the spring constant of a trampoline spring. Before I get into the actual measurement details, I want to talk a little bit about Hooke's law, kind of a review on that. It says the force in a spring is proportional to the extension. So what that means is the harder we pull or push on a spring, the greater the extension X. And it's related to the spring constant, like a very small spring that might be like in a ballpoint pen would have a very small K constant. A spring like could be the front end of your car would have a very large one, or like a trampoline spring, they're pretty large too. So that's what we're trying to measure, is this K number. And we're going to do that by knowing the force we apply and measuring the distance that it extends. So the objective of this measurement is to determine the spring constant of a trampoline spring. And the way we're going to do this is we're going to hang known masses and measure spring displacement. The instruments are pretty simple, just a 1 millimeter resolution ruler, and then I've got a gram scale that I measure the masses. And so the units are going to be in millimeters and the masses in kilograms, where we're going to measure things in. Okay, so this is the simple setup. This is, first of all, this is a sawhorse that I use in my garage. You can see all the paint on it. I've painted on it before, but it's metal, so it's pretty sturdy. And then I've got this is a millimeter scale, a metal ruler. And then here's the spring. And then here's the attachment where I attach the weights. And these are the weights down here. A little over 22 kilograms, around 47 pounds. You need quite a bit of weight to get that spring to extend. It is a very stiff spring. So this is a close-up, and this is going to be my first measurement of zero. So here's the spring itself. There's the connection that I used. I put two black dots on it right there so I can take two measurements of the extension when I put weight on it. That way I can average those numbers together, and that's one more way I can get a little more accuracy into my measurements. So the first one was 84 millimeters and then 45 millimeters on this lower mark. And this is with nothing added. So this is my 0 point. This is where I'm starting, an average of 65 millimeters. So now I added the first weight, which is 2.322 kilograms. Basically, it's just a small 5-pound dumbbell. That's what it was, what it is. And so the displacement in this top one was 83 and 44, so an average of 64. So you can see it's gone down very little. This weight, 2.3 kilogram weight, did very little to stretch the spring. But I'm going to add more. So now I added a second weight to it. I don't show, you can't hardly see it here, but you can see there's another chain that's connected to it. And it caused the spring to extend a little further. You can tell the spring's starting to stretch just a little bit. And 77 and 40 were the measurements here on the scale. Average those of 59. So we're getting some movement in the spring as I add more weight or mass. Now you notice, you can see the spring actually extending a little bit now. What I've done, I added a third mass, which is 7.07 kilograms, and that was actually just a 15-pound barbell or dumbbell with some chains on it so that I can attach it to here rigidly so it would not fall off. First measurement 65 millimeters, then 28, average of 47. So there's my third measurement. Now this is the fourth and final, so I've added here I actually added the boat anchor off my boat. I took that off. It was 7.079 kilograms. It's a little around 15-pound boat anchor. I added to that, and there's the 15-pound dumbbell, the 10-pounder, and then the 5-pounder. So those are the weights. This is around 47 pounds total, or a little over 22 kilograms is the mass. And then my reading, I didn't show you the little lines, but it was 53 and 15 divided by 2 is 34. So that's the final extension. So those are my 5 measurements. I've got the 0 plus the 4 weights that I added. So here's a table that shows the actual displacement, the average displacement, and you can see it stretched about 31 millimeters from start to finish on this experiment. And here's the mass that was added. That's a 0 point, first mass, second mass, third mass, and the sum of all 4 masses added together in kilograms. Like I said, that's approximately 47 pounds. Now I had to start doing some manipulation of the numbers to get in a proper format to graph this extension. So here was my mass in kilograms, that's unchanged, my displacement in millimeters, but what I had to do here is I calculated the extension. So basically what I've done is I calculate the difference between these numbers. Well, the difference between 65 and 65 is 0. It's the 0 point. And then I converted this to meters, divided by 1,000. So it's 0 meters. The first one, 65 minus 64 is 1. 1 is the extension in millimeters, 0.001 meter. Finally go down to the last one here. 65 minus 34 is 31. 31 millimeters of extension. That's 0.031 meters. So I'm going to need my mass, and I'm going to need my extension. Because remember, force is equal to K times X. This is the X, and then this is going to be the force. It's related to the force. The mass is. I'll show you how that's related in just a second. Okay, now we need to convert that mass to force. And we do this by the Newton's second law. F is equal to mass times G. And I've got a video on Newton's second law. I'll explain this. And so I just did this one example right here of the first mass. So it's 2.32 kilograms times 9.8 meters per second squared. That's the G number. That's the acceleration due to gravity. So we converted this mass of 2.322 kilograms to 22.8 newtons. We need our units of newtons because K has units of newtons per meter. So now we're going to calculate a K for each measurement now. The first one, we had a force of 22.8 newtons. It only had a 1 millimeter extension. It's a pretty rough number. That's not a good number. Too small. Too much error. Now, as we added more weight, we got a bigger extension, and this number started becoming a little more realistic. And so as we keep adding more weight here down to the final 208.8 newtons, and then we get the extension of 31, or 0.031 meters, that gave us the K value of 6740 Newton meters. That's getting more accurate. But the way if we really want to get a good number here is to take all these into account. We did a best line fit. So here's our force in newtons. And then this is the extension. And we saw it went up to like 0.031 millimeters, or meters, I mean. And then here's our force over here. So I drew a straight line through it, best fit using the computer. And the slope is the K value, 6456, or about 6.4 times 10 to the third, and that would be Newton meters. So what we got out of this using that graph, we got an approximate number between 6.5 and 6.7 times 10 to the third Newton meters. That's our spring constant, the K value. Uncertainty was fairly high here. It's pretty rough measurements, 10%. And what we observed was Hooke's law holds approximately for all small extensions. It's nonlinear, and if you pull too hard, you're going to break the spring, and then it will be totally nonlinear. Resolution limits precision at low displacements, and you saw how the 0.01 or the 1 millimeter extension gave a much higher K value than when you pulled on it and got a more accurate displacement and more accurate K value. So real springs show slight deviations due to coil geometry and friction, and also nonlinearities in the properties. I hope you got a little bit out of this video and learned how to measure the spring constant of a trampoline spring. If you did, give me a like, thumbs up, subscribe to my channel. I want to thank you for watching.